Good morning, everyone. Thank you all for coming. I'd like to begin by first saying welcome to our conference on the empiricism and the methodology of modern physics. I don't know how many years we've been doing these conferences, but certainly since the 90s. Many of you have been here throughout that time. So thank you all for coming again, or thank the rest of you for coming for the first time. I'd like to thank the Rotman Institute, the philosophy department, the Faculty of Arts, and the Western's Vice President of Research for funding for this occasion. And I'd also like to acknowledge that Western is located on the traditional lands of the One Spoon Treaty Territory, which is the ancestral territory of the Anishinaabe, Haudenosaunee, Lenape, and Shanongton nations. So this conference is in honor of, sort of occasioned by the last thing written by Bill Dimopoulos, his book on theories. Bill was our colleague, the colleague of many of us here or at other places like Oxford or Harvard or UC Irvine. He was the teacher of many people in this room. I consider him my teacher as well as my colleague for many years. And his influence on the whole history of this department is kind of summed up in the fact that we have this conference on logic, mathematics, and physics every year, because the combination of those three things is what always made Western a unique place in the philosophy of science. And Bill's own contributions to logic, philosophy of language, and philosophy of physics are a sort of unique combination of interests, all of which are in some way or another reflected in his book on theories, and we'll hear more about that. We're also here to celebrate or to make use of, more than that, the work of Howard Stein, who's also a huge influence on many people in this room and a contributor to Western in particular, not only by his visits, but by his close collaboration with myself, Bill Harper, Wayne Mervold, and many other people in this room whose careers gained something extremely valuable from Howard Stein, but especially this one thing. I certainly felt this when I first read something of Howard Stein's, which was his paper, Newtonian Spacetime. First of all, it made me feel like I really have to learn what an affine space is. And the second thing was that it made me feel like there's some combination of technical work in physics and profound philosophical issues. That's something that he had in common with Bill Dimopoulos, and that has shaped the way we think about the philosophy of physics, and certainly about Newton as a physicist and as a philosopher of physics. And finally, George Smith is a figure who was closely related to Howard Stein and Bill Dimopoulos, and was a huge influence on many people in this room, and a huge influence on the way we think about Newton. I would say perhaps the second, I guess one shouldn't rank them comparatively at all, but he ranks with Howard Stein as someone who has profoundly changed the way all of us have to think about Newton. And no one can really write about Newton's methodology without thinking about George Smith and his account of Newton's use of the relationship between theory and evidence, and the whole conception of turning data into evidence by theory-mediated measurements. That is really a kind of theme of this conference that has profoundly influenced the work of myself and many other people in this room. And all of these are people that we've recently lost. Well, Bill died about 8 years ago, Howard Stein last year, and George Smith. I'd just like to mention one other person who was close to all of those people and was closely influenced by Howard Stein, by Bill Dimopoulos. He was Bill's oldest friend, and he worked very closely with George Smith. And that's Michael Friedman, who very recently died. And he's worth mentioning here, not just because he's a friend of ours and a colleague who just died, but without him, Bill Dimopoulos' book would never have come into being, because Bill finished a draft of it before his death. And it was Michael Friedman took on that project all alone, basically, with a little tiny bits of help from the sidelines, but mostly it was his sort of final tribute to Bill that he saw that book through the press. And he's another person who's shaped the history of this department. And I don't know if anyone's going to talk about him today, but I thought he should be remembered as the last of Western's great philosophical giants who has left the scene. So anyway, without any further ado, I'd just like to introduce Simon Saunders, who's going to talk about principal and constructive theories of physical probability and the Bell inequalities. Simon has been here many times. He was a sort of colleague of Bill's during Bill's visit to Oxford. And he's just someone who's well known to anyone who's been interested in the philosophy of physics over the last, I would say, 40 years. And his work on Newton, on space-time theory, and especially on quantum mechanics has had a profound effect on all of us. Anyway, here he is, Simon Saunders.
Thank you. Thank you very much. Do I need to use this? No. Good, good. Thank you for those words. And I must say it's really a privilege to be here. I was extremely fond of Bill, quite apart from his intellectual influence upon me. Howard Stein... Microphone? Am I hard to hear? I can speak louder. There. Is that better? Okay, I'd rather not use the mic. I can speak louder. I thought perhaps this mic was amplifying, but no, it's not at all. Okay, good. All of the people that you've mentioned, Rob, were immensely important to me. So it's really a privilege to be here. And it's a great sadness of Michael Friedman's recent passing. Michael was a personal friend as well as a colleague, as well as an intellectual influence on me, quite formative. I do think of London Western as being one of the great beating hearts of philosophy of physics, to be honest with you. And it's been that way now throughout my entire professional life. So I'm glad to be here. So I'm speaking on something that I hope would have been of interest to Bill. I'm quite sure it would have been, although the conclusions may not be quite the ones that he would have favoured.
This will amplify you.
Oh, all right. So is that better? Sorry, I need amplification, evidently. Let me jump right into it, because I've got quite a lot of things to say. There's lots of moving parts, and they're all needed to keep the thing on the road. You know, if a wheel falls off, then that's it. So let me start immediately with my postulates. This is a principal theory intended as such. There is quite a lot of subtlety in these postulates. They're rather, the simplicity is somewhat deceptive. In number one, I'm not defining a sample space, I'm just defining an algebra of which Boolean operations are possible. Two is more straightforward, except it invokes this notion of a physical state. Well, what on earth is that? So the idea of these postulates is they become contentful when translated into an appropriate physical theory. But the idea is also that they can be applied really at something more like a pre-theoretic level, but one which nevertheless involves a fair amount of empiricism, one way or another. So I do think this talk was designed rather for this conference and for Bill's interests. The physical state, if one's got a general, just a sort of a common sense physical understanding, as is used in the background always in thinking about analyzing Bell inequalities and so forth. What is this physical state? It's going to need to be translated somehow into something. I'm going to give it the symbol lambda in a lot of this talk. Three formal criteria, that's straightforward. Four, and this is the real one that is very foreign to any normal understanding of what is probability. I've had mathematicians look at these postulates and they throw up their hands in horror and say, well, what on earth do you mean? What is this physical change and so forth? The whole thing is meaningless. So these are not axioms. These are not intended as axioms. They really are postulates. And their meaning will become clearer, as I say, when translated into a physical theory, or given a general empirical context. But I do want to say that 4 clearly rules out epistemic probability. I am assuming a sharp divide between physical and epistemic probability. I know that not all members of this audience will agree with this sharp divide, but it's perhaps there's a third way. I'm not sure where that would be located in my spectrum. But 4, I think, does rule out epistemic probability. You've got a couple of envelopes and they're mixed up. One of them's got a lottery ticket. One goes one way, another goes the other way. Remotely, Alice and Bob each get their envelope. When Bob opens his envelope, assuming no action at a distance, the probability that Alice finds the lottery ticket in her envelope is changed. It's either changed, increased, or it's decreased. And if there's no physical connection between the two of them, it seems then that 4 must be violated. Okay, I'll come back to this sort of example later on in the talk. Let's just look at the EPRB setup, B for Bohm. Alice and Bob shoot off. They've got a source, a pair of spin systems. Each one has their own spin system. They arrive, and here I've got a schematic diagram. I think those who have not seen EPRB before are not in this room. So I don't think I'll spend any time on it. Okay, so the typical conditions, parameter independence is one and perhaps the most important. And it says that Alice's probability of her spin outcome when she measures spin component A, the probability of outcome S can equal plus or minus 1, spin up or spin down. That probability should not be changed, should be the same if Bob were to set his apparatus to a different spin measurement, not B, but B primed. The conditional outcome independence says equally that Alice's probability should be unchanged regardless of Bob's outcome, T. And I think my claim, and I'll come back to it later on in the talk, is that both of these conditions can be motivated from my postulates, at least given that Bob can remotely change his apparatus setting without disturbing Alice's instrument setting. So there is a notion there of no action at a distance that has to be in place for these conditions to really follow from my postulates, and that's fine. These postulates are not intended to replace a condition of no action at a distance. Indeed, 4 could be satisfied if you take quantum mechanics, and if you think the quantum state is something physical and real, a part of the ontology, because that's what this Boolean business is about. Have I got a pointer that works? Yes, here. This Boolean business is really the ontology. So if the quantum state is a part of the ontology and the quantum state is subject to collapse, that's action at a distance, Alice's probability will change immediately on Bob's performing the measurement, collapse of the wave packet of the quantum state. So something has changed in Alice, and her probability can change. So my axiom, my principle A4 can be satisfied. But if you're working in a theory which explicitly has action at a distance at the level of the ontology. Okay, but now a third type of condition you might think also follows from my postulates, and that's what about lambda independence? I mean, my postulate 4 says that it allows that the physical state could be changed, and still it says that Alice's probability at x will not be changed. So this is really quite a strong constraint here. And that would suggest something like lambda independence. And that would seem to be nonsensical. Okay, so now the key point is lambda, this physical state, is it part of the ontology or not? And it's, I think, only when it is a part of the ontology that these postulates stand a chance of being satisfied. So that case, lambda independence, this lambda primed and lambda, you've got to worry about, well, to what extent is this lambda part of the ontology? Okay, so a change of topic. I've just given the basics of the principal theory. My new topic is a constructive theory, and this constructive theory, it's a standalone theory. It doesn't need the principles. Postulates, sorry, I equivocate between calling them postulates or principles, don't I? I should make up my mind. Anyway, so here is my constructive theory, my translation now. I think, I'm sorry, I've sort of, did I say that I was about to introduce the constructive theory? Sorry, I must first translate my postulates into the framework of the constructive theory, which is no-collapse quantum mechanics. So this is going to be Everettian. It is many worlds. But I don't need the apparatus, much of the apparatus of Everett or many worlds. I don't need to discuss or talk of observers or decoherence or the macroscopic at all. I only need, thank you, I only need no-collapse quantum mechanics, unitarity alone, the quantum state, no hidden variables. That's it. And so now start with number two, what is the physical state? Answer, a quantum state, and specifically a vector in Hilbert space. It does not normalize to one. It's got phase, complex phase, and it's got an amplitude, a real non-negative amplitude. And I'm considering an arbitrary representation of that state as a superposition of other orthogonal vectors. And that then is the physical state. And now the Boolean algebra, the ontology, is itself that state, as is appropriate in no-collapse quantum mechanics without hidden variables. Pretty well all you've got is the quantum state. That is the ontology, that is the physical state. So the two are, in some sense, identified. So specifically, the elements of the algebra consist of the components of the state in this expansion and their linear sums. And with those you have Boolean operations, you can take any sum of such vectors, consider the set of those vectors, and then set theoretic operations of intersection and union will give you the Boolean operations. Additivity, this is from postulate P3. So this is just straightforward, formal. The condition of orthogonality, disjointness that I've got here, it goes over to orthogonality of these vectors. And last but not least is this P4. What does it say? So if phi is unchanged under some unitary transformation, then its probability in the original sigma and psi must be the same as the probability of phi in this with respect to this new physical state and algebra. Okay, now on the basis of these translations of the postulates, there's a simple theorem. And the theorem is extremely general, as I think you can witness from my assumptions. So results like this have been obtained before, but usually in a much more specialized context, and usually with the assumption of really decision theory axioms, if only an axiom of some notion of equivalence, which with reflect to an agent who is given specific kinds of information and so forth. So what does the theorem say? It says vectors of equal Hilbert space norm, equal amplitude, have equal probability. And so this is to say that any notion of physical probability that satisfies these postulates, that assigns probabilities to vectors in a Hilbert space in an expansion, must then agree with this theorem. If equal in amplitude, they must have equal probability. Okay, so sorry, now it's at this point that I wish you to go to the new topic of a constructive theory that in principle, and this is how I originally developed it, is defined without any reference whatsoever to all of these postulates. Okay. Here's just a brief representation of the proof. If anybody wants to come back and inquire how this proof goes, I'll refer to this diagram. Okay, so here now is my constructive theory of physical probability. The key idea is that of an equi-amplitude expansion. So again, take any state whatsoever, but now it's not any expansion, it's an expansion into orthogonal states of equal norm. Okay, I call such states microstates. Now, what can you do with this sort of thing? Well, if you've got a projector and all your microstates are eigenvalues of the projector, then you can ask, well, how many of them lie with eigenvalue 1 for that projector, how many with eigenvalue 0? So if m is the number with eigenvalue 1 out of n in total, probability of that projector in this expansion is then m over n. So I sometimes meet people who say this is unintelligible. I sort of, it's the very sophisticated philosophers will be very, very careful to preserve what they consider unintelligible. But I do maintain that this cannot be unintelligible because the analogous condition that arose in the Everett interpretation back in the day with Graham in 1973 was where you have such an expansion, but you don't have equiamplitude conditions. These are just branches or worlds in the Everett interpretation. And you just count the number of branches, and that gives you the probability of some outcome, the number with that outcome. Now, everybody found that entirely intelligible, especially critics of Everett. So I will not accept that any critic of Everett finds this unintelligible. Now, there's lots of other reasons why one may not be happy with it. That's another matter. But I think it is intelligible. And indeed, if you then compute the Born rule quantity for P in that state psi, then you find that it agrees m over n. And indeed, this is then a frequentist interpretation whereby, given these special conditions, one has the probability for P in terms of the number of occurrences in the expansion. And if you chose a different equiamplitude expansion into n-primed microstates, m-primed of which are in P, then because the left-hand side is the same, you would have to conclude that m-primed over n-primed equals m over n. So there's a kind of uniqueness built into this. Okay, so this is fine. This is very nice, almost too simple to really be interesting, and meets the obvious objection, well, what on earth do you do when you don't have projectors that are so convenient to have microstates that diagonalize them? It's quite a constraining condition, the equiamplitude expansion. Typically, you will not find that the projection, you will not find an expansion that diagonalizes the projection. So what's needed is a different and a new idea. And that I call imprecise. Well, I called it interval probability, and then was told, no, it should be called imprecise. I didn't know that there's a whole field revolving around these ideas. Mostly, they're focused on epistemic probability. So doing it at the level of this so-called physical probability is perhaps a bit new. The point being that, with complete generality, this will be true for any projector P. This will be true. So some will be eigenvalue 1, some will be eigenvalue 0, but then there'll be these guys, which I call Schrödinger cat states for P, that will be neither. They're superpositions of P and not P. And it may be the case, of course, that J, the number with eigenvalue P, may be 1, 0. There could be none with eigenvalue 1. All of them could be Schrödinger cat states. So this would be extremely uninformative. An expansion of that type, none of the microstates diagonalizing P would tell you nothing about the probability of P. On the other hand, the other extreme, when they're all eigenstates of P, then you get an exact and precise number. In between, you've got this really a bound. You've got a lower bound on the probability of P and an upper bound. The lower bound is set by the number of microstates that have eigenvalue 1, the upper bound by those that have eigenvalue 0. And the interval between the two is the imprecision, if you like, in the probability. And now another simple theorem. All of the theorems I've got are so simple, they're really embarrassing. You shouldn't even be called theorems. I don't know what else to call them, though. So the Born rule quantity lies within the interval. The Born rule quantity obeys is equal to or greater than the lower bound, less than or equal to the upper bound. Okay, so now a couple more theorems, again, extremely easy to prove. The first one says if the dimensionality of the Hilbert space is greater than 2, we always have that condition, don't we? It always comes back. Anyway, so greater than 2, then you, for any vector whatsoever, you always got not just one equiamplitude expansion, but a continuum infinity of equiamplitude expansions. If that's puzzling to you, think of the physical state as a given direction. You've got 3 orthogonal states that sum to give that original state, and of course you can just rotate about that original vector and thereby get a continuum infinity. But the point is that for any n less than or equal to the dimensionality of the Hilbert space, of course, you can then get equiamplitude expansions of n orthogonal elements. The second theorem concerns projectors of a rather more specialized type. They're those that have infinite range. So these are projectors onto a subspace of Hilbert space of infinite dimensionality. And if those strike you as being a little bit restrictive, well, they're not restrictive for any physical system which has got spatial properties. If it can be localized at all in space, you're looking at something like an L2 space over some interval of the real line, and however small that interval of the real line, that L2 space will be infinite dimensional. So you take a molecule, I don't know, an atom, an elementary particle in intergalactic space in an empty universe, it will still have to have an infinite dimensional Hilbert space if it's going to host a notion of location and so forth. The canonical commutation relations, of course, require an infinite dimensional Hilbert space and so forth. So I offer no apologies. Well, I sort of do, don't I? I've just given one, really. But I'm not really apologizing that this is restricted to projectors of infinite dimension. That does cover all physical applications of concrete physical systems, but it doesn't cover models, and these models may be important, spin systems without any center of mass degrees of freedom at all, perhaps a finite set of such, and so forth. It doesn't cover those. I do have a prescription for such theories, but if it comes up in Q&A, I can perhaps explain what are the pros and cons of that. Okay, so for such a projector anyway, then for any state psi, you can always find an expansion, all but one of whose microstates are eigenstates. Just one Schrödinger cat state. And now, if you consider for any projector, for each value of n, such an expansion, I'll say adapted to P, and then consider the limit as n goes to infinity of those I probabilities, those interval probabilities, the answer is the Born rule quantity. Okay, now there's something, perhaps let me say it now, that's rather important. For those who are very familiar with standard arguments against frequentism, classical frequentism, the point about classical frequentism, well, what's the ensemble? It's got to be spread over space or time. It can't be all in one place. Typically, one thinks of a repeated experiment. It's spread over time. And if you look at the infinite limit of such an ensemble, so-called hypothetical frequentism, that infinite limit may be different from any frequency in any finite subsequence. And that is very, very damaging to classical frequentism. It doesn't apply here. And that's quite interesting. The point being, you take any n, especially if n is large, you've got you are boxing in the physical probability, the limit, you're boxing it in to within 1 over n. N could be Avogadro's number. Avogadro's number to the power of Avogadro's number. There's no limit to how large n could be. So you can specify, for a finite ensemble, you specify the limit to arbitrary accuracy. So this is entirely different from classical frequentism, and maybe one shouldn't be calling it frequentism at all for that reason. Have I got a proof of the Born rule? No, I don't think so. It's a conception of physical probability in which the Born rule follows, but I can't really call it a proof, or at least certain people like Lev Weidman have absolutely and adamantly told me that under no circumstances can I claim this to be a proof. I do take the point. The point being, of course, that you've got to understand this sort of thing as really telling you something about probability if you're going to derive the Born rule. But who says these are probabilities? And it all goes back to the equi-amplitude expansion. Who says equal amplitude equals physical probability? And of course, the point is my postulates say. So at this point, evoke the postulates. Indeed, this then becomes a theorem on the basis of these postulates, or rather their translations into no-collapse quantum mechanics. This then turns into a theorem relating to this, which I claim to be intelligible. I'll take no negatives on that one from any anti-Everettian. Now, a pro-Everettian like Lev is a bit more difficult. When he tells me it's unintelligible, then we tend to end up shouting at one another in the friendliest possible way, but anyway, that's it. So anyway, the claim is that this then becomes really a theorem that upper and lower bounds on physical probability understood in these terms of these postulates, this then becomes a theorem. So I do claim I've got a proof of the Born rule. And actually, if you look at these premises, they don't say anything about non-contextuality. So it's a bit, well, this is very strong. But Gleason's theorem obviously does require non-contextuality. And now, further, I claim I get the constructive theory of probability. So I haven't done very much. I've only dealt with projectors. I've got to deal with self-adjoint operators. There's a lot more to do. But I do claim that this will give us a constructive theory of physical probability founded on these postulates. But then, and most important, this constructive theory does entail every single postulate when translated into no-collapse quantum theory. So including things like these formal criteria, I mean, perhaps some people would say the only attractive feature of classical frequentism is that Kolmogorof's axioms follow automatically. If you're looking at fractions of an ensemble, those fractions have to be bounded by 0 or 1, disjoint fractions have to sum, and so forth. But also the Boolean properties, synchronicity, the formal, but this one too. And this needs a bit of work to get out from this equi-amplitude expansions business, but this intrinsic thing follows as well. And this is so far without any mention of locality. Nothing that I've said has got anything to do with action at a distance up to this point, which again is to say that these postulates do not involve locality or no action at a distance. They're proved from a constructive theory that makes no reference to whether or not you've got action at a distance. Okay, and it's really looking at this sort of rather strange interrelationship between these two that made me think, well, it is a bit like constructive versus principal theory. I mean, I didn't really set out to create a principal theory, but it was very reminiscent of it. You know, one has Einstein's postulates, light principle, relativity postulate, and those in some sense imply SR, but treating rods and clocks as unanalyzed primitive things. And then you have a constructive theory that would be perhaps it would have to be a theory of rods and clocks, including rigidity. It had better be quantum, but based on Minkowski spacetime. So that would be then the constructive theory. And the constructive theory, of course, implies Einstein's principles, the light speed principle and the relativity principle. Anyway, there's more to talk about. I don't know. Maybe this comparison, maybe the comparison with Einstein and SR is rather superficial. I don't know. I'm ready to be talked out of it, but I found it helpful as a way of thinking about the relationships between the postulates and the constructive theory. Okay, so now let's go back to EPR and specifically look at the constructive theory. And these two conditions, parameter independence, conditional outcome independence, now assume no action at a distance. Okay, now this comes in. And it comes in, well, one could do it, relativistic quantum field theory, why not? You know, some people have even been brave enough or mad enough to try. I did once, and some other, Bob Weingart did at one point. But anyway, several people, Michael Redhead at one point, have tried to do EPR in relativistic quantum theory, but it's a bit silly would be harsh, but premature perhaps, because the obvious thing to do is to work with a tense product structure with Bob and Alice, the different factors of the total Hilbert space, and each is restricted only to local unitaries. So, and thereby there implement the requirements of no action at a distance. You can worry about the relationship of that to a relativistic quantum theory at a later point if you really want to. Okay, so if we then ask, well, what does lambda, I'm calling this lambda many, now that it's equipped with locality constraints in this form. One can ask, well, what are these quantities according to lambda many? Answer this. Alice's probability of spin-up is the fraction of microstates that diagonalize her projector, the relevant projector. And now the conditional probability, what is Alice's probability of spin-up conditional on Bob getting outcome T, is just by the definition of the conditional. It's given by this fraction. I'm going to come back to the relation between these two things later on. Of course, what conditional outcome independence is telling us is that this thing, which is this thing, which is this thing, equals this thing, which is this thing. Okay, so this and this are supposedly equal by outcome independence. Why should that be? Well, I'll come back to it. Anyway, the obvious claim to make now is that lambda many satisfies parameter independence. Of course it does, because if you're going to look at expansions, equiamplitude that diagonalize Alice's projector, it's just the identity here for Bob. It doesn't matter what Bob does. It doesn't matter what the situation is on Bob's side of the apparatus. So no problem. But there's a problem. There is a problem that comes if you think, well, what happens in pilot wave theory? Okay, so now what people will realize, what I've been treating lambda here, I've been treating it as the quantum state, psi. This is a so-called stochastic hidden variable theory in the terminology back in the day, in Bell's time in particular. But the alternative is where the lambda is a hidden variable, which is a deterministic hidden variable theory, where all of these probabilities are zeros and ones. You've got a probability distribution over the lambdas, which is set up by the source. It's the state preparation device, dictates what this rho is. And you compute, sticking these things, which are all zeros and ones, into here, you thereby compute probabilities on repeated experiments that will be reflected in the statistics of outcome. Now, when you go through all of that, in the case of pilot wave theory, what you find is at this level, the probabilities, indeed, parameter independence is satisfied. As it must be, if parameter independence were violated at this measurable level, you would have superluminal signaling. So yes, parameter independence is satisfied. But at the level of the individual Bohmian particles, the Beerballs, at those individual, each case for the experiment, parameter independence is violated. There is explicit action at a distance. You can see it in the equations yourself. You can see how this thing does not stay the same when you change the setting of the remote device. That change of setting the remote device affects the state. It affects, by the guidance equation, the various velocities of the Beerballs and Bob's end of the experiment, and those in turn affect the velocity of Alice's Beerball as it goes through her apparatus, and thereby the outcome. Now, could something similar be going on here? I mean, with lambda many, we have the probability, fine, parameter independence satisfied, but what about the individual microstates? Can the individual microstates nevertheless exhibit action at a distance, as they do in pilot wave theory? And I think those of you who think about this just for a moment will realize, well, they've got to. Well, I don't know which one of you has sort of figured this out. They've got to. The individual microstates can't satisfy both of these guys, because if they did, then the Bell inequalities would follow. But we've got a theory that supposedly gives us the Born rule, violates Bell inequalities. So you see the problem. So look, let me just go over how these theories are going to be related. The idea is, suppose lambda is randomly chosen from the appropriate equiamplitude expansion on each experimental run. You repeat the experiment and you build up a statistic. So that's really saying that this thing now has got to be the equiamplitude expansion over here. And rho, of course, will be flat. Its equiamplitude and equiprobable rho is just constant. And this actually shows that rho satisfies the usual condition that it be independent of the settings for the measurement apparatus. Right? That's what rho's got to do. And rho is always flat. Whatever this thing, rho is always flat. But what does change is the domain that you're integrating over. That's what changes. Okay, and now let me just to really sort of make it all terribly intuitive. Sometimes that's perhaps something to be distrusted, but I think in this case it's not. So I've got the ball in an urn model of probability. Someone actually, Rob, that you didn't mention is Itamar Petoskey and his connection to London as well. And Itamar, I have to say, out of all of these people mentioned, had the greatest influence upon me. I thought his book on probability and quantum logic was an absolute masterpiece. And he used this metaphor in that book. So fine, balls in an urn, spin up a red, spin down is blue. You randomly select them one at a time. Well, you're supposed to have replacement, but I couldn't really draw that, and I'm no good at animation, so I've got them all on a plate. We can make the number of balls just enormous, and then you don't have to replace the balls back in the urn. And you build up, by repeated experiments, a little sub-ensemble. And the idea is that sub-ensemble, the relative frequencies, the statistics, will be the same as in the urn with high probability. You can't get away from that. Not with certainty, not approximately, but with high probability, where the probability is determined by this rho lambda in the first place. Okay, oh, and whilst I'm at it, remember the Schrödinger cat? There's always a Schrödinger cat microstate. There it is. I've just put it in there. It's a little one. Chances are you won't pick it out. If I make the number of balls in the urn Avogadro's number, I'll never pick it out. It'll never be on the plate. I don't have to worry about it. Okay. So now what all of this should do is set up a worry, because first the worry, microstates cannot satisfy both parameter independence, conditional outcome independence, because otherwise you get Bell inequalities. But parameter independence already seems wrong. And the reason it's wrong is because the lambda, you've got the lambda in the context B primed, and the same lambda in the context B. So how can you have the same microstate when you've changed the setting? Because the microstate, it depends on the A and the B. So this really is the clue. What is going wrong here? It's not so much that the microstates show actions distance. It's that this parameter independence condition isn't the right way of formulating the criterion of no action to distance when lambda is itself ontologically contextual. So always it was assumed, of course, lambda must be contextual vis-a-vis the probabilities that it defines, especially deterministic, otherwise you'd fall, Gleason's theorem would rule it out, must be contextual. But what people didn't seem to think in Bell's time was that the lambda could itself be ontologically contextual. So I'm ready to be corrected. I have asked various people, Harvey Brown, Jeff Book, various people who knew the times well, was this ever discussed? And it seems that it wasn't, but I'm waiting for Wayne's verdict. Wayne, I'm waiting for your verdict. Anyway, so let's just put up on a little table the situation for lambda many at the level of probabilities satisfies parameter independence. Lambda 1, just looking at individual microstates, does not. Pilot wave at the level of probabilities satisfies parameter independence. The individual microstate, not microstate, Bohmian Beable, it does not. And then conditional outcome, again, so they're very similar, lambda many and lambda 1, with pilot wave theory and so forth. But now there's this question of lambda independence. So look, at this point, I'm going to go quickly, because if I really explain it, it'll take me 5 or 10 minutes, and I'll get hopelessly behind. So forgive me if I'm really quick. Again, it's something I can come back on. But the thought is this. Here is the relevant equi-amplitude expansion for A and B settings. Here it is for A and B prime settings. The microstates have got to diagonalize the two spin measurements. So they're of this form. Or with A and B prime, they're of this form. Now and of course lambda, if it belongs to one of these, can't belong to the other. Okay, so this is what I've already been saying, but now we're seeing it explicitly. The thing now to note is that the difference in the ensembles only affects the second factor. It doesn't affect the first factor. And in fact, the number of elements here with the first factor plus 1 is in 1-1 correspondence to the number in here with factor plus 1. And that sets up a framework for talking about counterfactuals, whereby, and let me just put it, whereby given this constraint on lambda and lambda primed, this condition is indeed satisfied. Okay, so now that is also satisfied by lambda 1. Sorry, I should have said this condition can be satisfied, can be set up without reference to lambda many altogether. So this condition, if you've got a bipartite structure to lambda, I'm backing away from theory. I'm looking at just the general ordinary framework of Bell inequalities. Supposing the lambda's got a bipartite structure, then one can express this sort of condition, and then it could apply to many other different theories. But as applied to lambda 1 in particular, no surprise that it's satisfied. So I've got a tick here. Now, if you could do a tick here for pilot wave theory, maybe you could find some way of reconciling yourself to the action at a distance in pilot wave theory. But I don't think it's possible because it's absolutely explicit. You can see the action at a distance. So I don't think you can do anything about it. Okay, so this constructive theory of physical probability lambda many, putting aside pilot wave theory and lambda 1 and that stuff, just look at lambda many. So the claim is, this is the situation. We've now got to worry about, this has been safeguarded. I hope I've convinced you, 100% confidence now. There is no action at a distance, not at the level of the superposition of all the microstates, nor at the level of individual microstates. That I hope to have convinced you of. What about conditional outcome independence? Now, a related condition is completeness. If you look at the definition of the conditional, then you see that given this and completeness, you get conditional outcome independence, or given the conditional outcome independence and the definition of the conditional, you get this. So they really go back and forth with one another. What is going on? So look again at the definitions of, I had these up on a slide 10, 15 minutes ago. And the question is, why should this quantity equal this quantity? Well, here's the way to think about it. So here I've got, I'm graphically representing the spin, Bob's spin t equals -1. This is the number of microstates. The microstates, you can think of them as lines in here. And here for the spin, if this is spin down, this is spin up, lines in here. And the fraction of microstates in here divided by the total is then the probability of this, and so on. Now, what about Alice's projector? Well, if it's sitting here, so that all of the microstates that make Alice's projector true for spin up are contained in Bob's spin up, then indeed this quantity will equal this. I mean, maybe you just need to have a moment to think about it to convince yourselves that that's true. And if you've convinced yourself that that's true, then you'll say the same follows here. If all of the microstates that make Alice's projectors for spin, whatever, S, true, are contained in the microstates that make Bob's t equals -1 spin down outcome true, then this conditional outcome independence is satisfied. So this is the thing that violates the conditional outcome independence. And if you think what it's saying that some of the microstates that make Alice's spin up outcome true come from Bob's spin outcome being false, being spin down, and some come from Bob's outcome being spin up. That, as it were, contributing to Alice's spin up outcome are microstates that involve both Bob getting spin up and Bob getting spin down. And that would be a nonsense in a one-world theory where there's a unique outcome produced by Bob. If there's a unique outcome produced by Bob, you're either in this area or you're in this area. So I think very clearly this issue of does Bob produce a unique outcome is related to conditional outcome independence. Okay. So, of course, what about the violation of conditional outcome independence? So it is violated. So what does that mean? But then there's a well-known meaning. It means that the state is a product state when it's satisfied and is an entanglement when it's violated. And you can simply see that looking in terms of microstate counting, but let me not spend time in the details because I think I'm going over time. All right, so complete outcome independence, I claim, is the right condition if Bob produces both outcomes. What should happen on the basis of no action to distance is Alice's probability should not be affected by Bob's outcomes. Both outcomes should not affect Alice's probability, and indeed it doesn't. This is satisfied, and on this basis, so I claim, lambda many is perfectly free of action at a distance. Perfectly free. I'm not saying perfectly free of non-locality, entanglement, non-separability, there's something non-local about that, but it's free of action at a distance. Okay. Well, I could end now, but I think, in a way, the most interesting aspects of Bell inequality and Bell inequality violation, I mean, if this were true, it would show that it was all a big waste of time, really. You know, all that it turns out to be is a test for entanglement. And we've got other criteria for entanglement that are more easily used in the laboratory, especially in high-energy physics experiments, which is stuff that's recently been worked on. And what was the Nobel Prize for, and so on and so forth. So, of course, the real interest of Bell inequalities and their violation is the generality of the assumptions that imply the Bell inequalities. Because then, from the fact that they're violated, you get a negation on one of those very general assumptions, and that's extremely interesting. So for that purpose, go back to my principal theory, and now include locality, no action at distance in it. Okay, and in particular, just perhaps think again about what Bell said. So this is, I think everybody knows this diagram. So full specification of everything that happens in this region 3 means you know everything there is to know about region 1, Alice. Doesn't matter what happens in region 2 whatsoever. Okay, fine. But I just want to point out the way that Bell actually frames this. He speaks about unaltered by specification of values. He doesn't really care how they're specified. Any specification could go on, which actually sort of suggests it comes back to my lambda independence condition. Bob can just specify his lambda. Oh, heavens, I've just realized. I haven't told you why we should give up on lambda 1. I'm sorry. Oh dear, that was remiss of me. I mean, lambda 1, it gave us everything we wanted. No action at a distance. One world theory. Violates Bell inequalities. What's wrong with it? Well, Bob had to control his hidden variable. He had to change it depending on his instrument setting. And this wasn't by normal interaction going forward in time. No, this comes under the general umbrella of a retrocausal theory. What's wrong with lambda 1 is retrocausation or superdeterminism, one of the two. Sorry, I should have made a big point of that, because otherwise, goodness, lambda 1 would be everything that we want, wouldn't it? Coming back to Bell now. So Bell allows this business of specification of values, and so maybe Bob could just specify his state. So really, Bell isn't actually ruling out lambda 1. So I put that just on the table. I mean, I'm happy to be proven wrong, but it would be striking to me, because Bell, after all, did very strongly insist that this stuff, what he called local causation, was flat out inconsistent with quantum mechanics. He did speak about superdeterminism, but it's not, and what's wrong with superdeterminism, which sort of but it's not in here. Anyway, okay, so let's just have the conditions, and here's the physical state independence, where this specification, maybe Bob just specifies his lambda, but no, retrocausation is ruling that out. And now complete outcome independence is on the table as well. That's the question. Is, from the point of view of my principal theory, is this notion that Bob's remote experiments does not produce unique outcomes, is that even on the table? It wasn't in Bell's day. Hardly anybody talked about Everett. I mean, Bell was one of the very few, and what he had to say about it was pretty scathing. So it just wasn't on the table, so it was no part of the reasoning that led to Bell inequalities. But now I suggest it really does have to be on the table. I think otherwise it just becomes dogmatic. You're just ruling out many worlds as a matter of dogma. Once it is on the table, then I think there's a very interesting debate to be had about, well, which of the two conditions does this hold? Or does this hold? Because remember, Bob, in doing his experiment, he produces two outcomes. Well, you might think each outcome is itself a change that's produced by Bob. So why shouldn't Alice's probability be independent of that change? Even though there's another change produced by Bob, which was the other outcome. So there's room for debate here, and I think it's quite an interesting debate. But I'll not do it now, because I don't have time. Okay. Here's the logic, though, that I think reasonably follows. Given uniqueness, then no action to distance, no retrocausation. Given uniqueness, we get Bell inequalities. And this, I say, all follows under the ambit of my theory. Do we need my little principal theory at all? Some people say this conditional holds regardless. So Weigel and McQueen recently have a paper on this. Several people have argued this. Lev Weidman, I think, has argued for something like this for many years. But does it need PP? Well, I think it does. And in justification of PP, note here how Bell frames it. The probabilities. It is all about the probabilities. So Einstein, causal, local causation, it doesn't speak about probabilities at all. So probabilities just come in sui generis, really, in the usual discussions of Bell, whereas I'm introducing probabilities in a very explicit sense. So I sort of stand, I think PP serves a function here, and it adds clarity. That's my claim. Others may disagree. And now, of course, this thing is logically equivalent to this. And given that no action at a distance is about the best attested principle in all of physics, one might think that the failure of Bell's inequalities should not be turned on the locality, as Tim Maudlin wishes to do. No. It turns on the uniqueness. We should conclude non-uniqueness. Do I have another 5 minutes, or have I gone over?
You have gone over.
Oh, then I'd better stop, hadn't I?
Depends on how much time you'd like to give.
Well, I do.
20 minutes.
Okay, well, look, I tell you what, look, because this has also got a bit of a tribute to Bill, let me just make a comment on the Einstein photon box paradox. And again, we've got a photon, it's entangled with these two boxes. Alice and Bob shoot off, each has got a box. They arrive, and now Bob opens the box. If Bob has a unique outcome, then by these postulates, Alice's probability, this is just like the envelopes in the lottery ticket. Okay, and the conclusion, the right conclusion, is that my postulates are false. Okay, but if Bob opens the box and what he finds is something else, it's a cat in an indeterminate state, but we'll hope it's between being asleep and awake. And given that Bob produces a superposition of finding the photon and not finding the photon, then the right conclusion to draw is rather that PP, again, implies that if no action's distance, then no uniqueness. Okay, I did just want to include with a comment on Bell. He did say, and I don't think he was, as it were, entirely without an open mind, and yet, of the many-world interpretation, it may have something distinctive to say in connection with the EPR puzzle. I hope that I've shown that it does, although I can't help but feel it's the conclusion Bell would have least liked. I don't know. Right, so thank you, in fond and admiring memory of Bill, and here are some papers which are relevant to what I've talked about.
So we have time for some questions. Any questions, comments? Wayne? Yes.
Thank you, Simon. This was really lovely, and I think I'll have to spend more time trying to really digest it. I mean, I've often sort of wondered what one could even formulate locality conditions in the context of an effort and thing, and I think this is really good. Could you go back to the slide where you've got, when you talk about lambda many and you've got check marks and...
Yeah.
So parameter, so for lambda 1,
Yeah.
there was a problem with parameter independence because you just got simply like a different sample space depending on A and B, right?
Well, the original problem with parameter independence is it could not be satisfied along with conditional.
Right.
Because deterministic, you always get outcome independence of deterministic. So if these two, it's got to violate this. Right. But then you realize that this condition is ill-formed.
Yeah, in the context of lambda 1, that condition is ill-formed because A and B simply pick out...
B and B primed.
B and B prime pick out different sample spaces, right? Yeah.
Different lambda.
Right.
Yeah.
Whereas when I'm talking about lambda many, I can talk about a single sample space to take my microstates from...
No, excellent, good, yeah. So, and this is a very good question, because in a way what I've sort of argued and shown is that the superposition all of the microstates is not hiding, is not concealing an underlying action distance from each microstate. But each microstate has this context built into it. So, and I call it retrocausal. So is the superposition concealing retrocausation at the level of individual microstates? And in a way, this is a very interesting question. And there is a way of formulating this, and I did it myself 15 years ago without having any of this stuff in mind, in terms of my picture of divergent branches in Everett as opposed to overlapping branches in Everett, that you sort of do weirdly. Let me talk about what I did 15 years ago. So, but just on this, the obvious thing to say is that the quantum state is evolving through the measurement process, and it develops into a superposition which has nothing to do with my stuff, nothing to do with what I'm talking about here. It's all to do with decoherence. It's all to do with the engineering of the experiment, the design of the experiment, the interaction Hamiltonian, and the initial plate separation device, and so on and so forth, as to what Everettian branches are produced. My stuff just kicks in right at the end to say, okay, you've got this big superposition, fine. What are the probabilities? Now represent that superposition as a superposition of microstates of equal amplitude. And you do two things. First off, the microstates are then adapted to the outcomes in question. And the second thing is, well, you've got a count. And that count then gives you the probabilities assigned to each branch. So no, there's no retrocausation. What the microstate amplitude expansions are doing, they're not telling you anything about provenance. It's telling you nothing about dynamics. It's just taking that instantaneous state and it's telling you what probabilities of certain projectors have in that instantaneous state. So I claim there isn't a concealed retrocausation going on. Sorry, long answer, but does that address your question?
Yeah, I have to think more about this
Yeah.
to really understand what's going on.
Yeah.
But thank you.
Thanks, Carlo?
Thank you. Is it on? Ah, the tools. Oh, it's very complicated here. Okay, sorry. Well, first of all, thank you very much, Simon. This is I read your paper the last couple of days. It was very hard for me to read, and so I got a vague idea. Now it's much more clear.
Oh,
and so I have two very short comments that lead to specific questions, which is just my confusion. It needs some clarification, and I think you can give it. The first comment is that. Of course, since I've been working on a relational way of thinking about quantum mechanics, I've been trying, while both reading your paper and listening to you, to translate, and it seems to be completely translatable to some extent. I'm not sure about the language use, because there's this sort of metaphysical commitment to the ontology of something which, but everything goes through, and your both your postulate, how you call it, postular principles, can be used in another context, and the final list of implications can go through, and the non-uniqueness as a result, it's makes me cheer in a sense. Now, a second comment, which leads to the question. At some point when you presented your, and this it opens to my confusion, your principle, you said, well, there's no contextuality said explicitly here. There is contextuality, of course, because in some sense, because you're talking about Boolean algebra. The first word of your slides is Boolean.
Yeah.
Boolean means something is picking up something.
Absolutely.
Something is picking up a subalgebra, which is a commutative subalgebra here, of course. And I'm happy.
But I've got to just stop you. I didn't say there's no contextuality. I said that non-contextuality is not assumed. It's non-contextuality that is not assumed. Gleason assumed non-contextuality.
Yeah, absolutely.
So yes, this involves contextuality.
Which means, contextuality is playing a big role here, of course, in a sense. It's a contextuality.
It's
so. Let me go to your entire thing here, it's based on the idea that there is a Boolean algebra. So it requires a story which you're not talking about explicitly. You've talked somewhere else, and people doing the kind of interpretation you work on, is that, tell me if I'm right here, in an actual experiment of set of experiments, there's something going on, there's the coherence, blah, 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 and there's some Boolean algebra which is picked up by this other part of the story. Do I understand correctly, or am I missing some pieces?
Yeah.
Because if it's not that, what is that Boolean algebra? In a sense, what you're saying in a very sort of stupid version, poor man version, is that the lambda many is what brings in the dependence of what you call the state knows about Bob choice of T. Do I get it right? Or do I get it wrong?
Can I comment?
Please.
I hear where you're pausing, and I absolutely understand the worry. Now,
good.
The point about these equi-amplitude expansions, say again, you can use any basis whatsoever as long as you get out microstates with
fine.
Yeah, and it need have nothing to do with decoherence. It need have nothing to do with any measurements. We could be performing measurements, but I could be wondering, oh, what happened to that? There's an atom of cesium in this whatever, some sort of chamber or other. What about that? And I can ask, well, what is the equi-amplitude expansion for that? Forget about the experiment that's going on. But if I'm interested in specifically the outcomes of an experiment, then I'm looking at projectors representing those outcomes, and those projectors will be dynamically selected by decoherence. They will be favored by decoherence. Decoherence is really giving us ontology in the sense of tables and chairs and all of this stuff. So if you're interested in that sort of stuff, states, matter of facts about things like tables and chairs, stuff that is defined really by decoherence, then you choose an equi-amplitude expansion adapted to those projectors, which will mean in the decoherence basis. So you get then a sort of an alignment with the equi-amplitude expansion with the decoherence basis, but it's not forced upon you. It's only insofar as you're interested in knowing the probabilities of projectors in the decoherence basis. If you're interested in those, then the equi-amplitude expansion had better be in that basis and will then tell you those probabilities. In the general case, you might ask, well, where does the Boolean algebra come from? Well, just give me any projector you want, and I will define the Boolean algebra like this. I've got the physical state psi. I take p psi, that's a vector. I take 1 minus p acting on psi, that's another vector. And that's it. That's my Boolean algebra.
Right, but do I understand correctly that the probabilities that you're talking about, they are not probabilities on given what you call a state on the ensemble of quantum mechanical variables, just on a
just
after a choice. This is the same discussion as the old with its the coherent histories. So you choose a Boolean algebra, and then probabilities are well defined, of course.
But it's as it were. I'm in the situation. One way to think of it is probability is kinematics. It's built into the kinematic structure of quantum mechanics. We're familiar with that. The quantum state, it builds in both momentum and position. And it does that because if you expand in the position basis, it's the complex phases that are building in the momentum. And this is a beautiful, wonderful thing about quantum mechanics. And what I'm saying is it also builds in probability through equi-amplitude expansions. So it really is specify a projector you're interested in, you can then determine the probability.
Yeah, I get it.
As it were,
I get it, yes.
Tell me what you want to know, here's the answer. So, and of course, typically what we want to know are the probabilities of outcomes of experiments. So that's what sort of locks us into the decoherence basis and blah, 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 blah. But we could ask questions, as I say, there's that molecule, of cesium or whatever.
No, it was another question. Another question was
in the middle of the, right.
Thank you.
Yeah.
It's still on. Michael? I think this is still on.
Thanks, Simon. That was. I really liked that quite a lot, actually. And or to say, I think I did. So I'm going to have to have a closer look at your
Watch
papers.
out. It'll take you to Everett, I'm afraid.
But I just wanted to make a small comment question on, I think, the same slide that Wayne was commenting on, where you mentioned lambda independence.
Yes.
And I think when you gave the slide, you mentioned something to the effect that Bell never explicitly considered something like that.
Yes.
But I thought he did. Like, doesn't he implicitly consider that when he criticizes the Koch-Specker theorem?
Right. Yes. So this is where this notion of contextuality in an ontological sense really existed in the literature right through that period, late 60s, 70s, into the 80s, was Koch-Specker. But it didn't cross over into the literature on Bell inequalities, except in the writings of one person. Wayne, tell me who that person was.
Say that again?
The notion of contextuality that existed in Koch-Specker right through the 70s and 80s, that talk of contextuality did not make it over into Bell inequality talk, except in the writings of one person. You know who I mean. It's Abner Shimoni, of course. Yes. His 84 paper, his brilliant 84 paper, where he went into this in great detail, because anyone who read Bell 66 could see Bell was talking about contextuality, but Bell never used the word. The word contextuality.
Abner coined it.
Yeah. Did he? Even
yes, he did.
I would also mention
there we go.
David Merman. So David Merman talks about this.
But not in connection with Bell.
He does.
Does he?
He does.
Oh, thank you.
I think it's his 94 paper.
In 94.
I read it in Wayne's class.
Yeah, but Harvey Brown did in 92. Yeah. I mean, this was following Abner. It was Abner's 84 paper.
Right, Abner was.
That really, and Abner said of Gudder, his 72 proof, was it 72 or 68 or something, that showed you can always construct a hidden variable theory that recovers quantum probabilities. And looking at it, it was contextual. And Abner described Gudder as showing contextual hidden variable theories could be found that satisfy Bell inequalities, violate Bell inequalities, and so forth. So it was really Abner who put contextuality into this literature. But not everyone followed. I mean, Michael Redhead's book doesn't mention it. Tim Maudlin's book, 94, doesn't mention contextuality except in Koch-Specker. So yes, there's a very interesting further conversation to have about, well, what is this notion of ontological contextuality? How does it match up with what goes on in Koch-Specker? And indeed in the non-probabilistic proofs of action at a distance. I mean, I haven't mentioned those. So there is a lot more to say.
Thank you.
Have other questions? Any other questions? For anyone? Wait. Okay.
I used to have a little worry about the way you're expressing things towards the end. So you talk about Bell's condition of causal locality, and you're glossing that as no action at a distance. But I think the local causality, okay, and the difference is important. So local causality, I think the name is appropriate because it's not motivated only by locality conditions, but also by causality conditions. It includes the idea, something like that any correlations are explicable by something like a Reichenbach common cause. And I don't think Bell thought that was a consequence of locality alone. So I think for people like Tim Maudlin and Travis Norton want local causality to be just locality. But I think in Bell's mind, it was locality plus something like a common cause principle. And part of my evidence for that is he was a big supporter of attempts to make genuinely relativistic collapse theories, with no trace of any dependence on the preferred foliation. And it's hard to see, how that could even make sense if you thought that violation of local causality was the same as action at a distance.
Yeah, I think I'd look forward to discussing this more. I hear you, and there are subtleties in this, no question, which I haven't addressed. Yeah. Yeah, I think that's right. But I don't think. I mean, it's rather important.
Nothing you did depends on
No, it probably doesn't. But here's the thing that surely is terribly important, isn't it? That if we think of what no action at a distance is connection with field theory, you could have a non-local field theory. I mean, the classical de Broglie equation could be thought of as such, but certainly in a relativistic case. So that notion of locality, which is clearly related to no action at a distance, that fields are local, that you have microcausality in quantum field theory, this is clearly involved in no action at a distance, but it equally clearly does not rule out entanglement.
Mm-hmm.
That's the thought. So this business of non-separability, yes, it's a kind of non-locality, but it's of a kind that is nothing to do with action distance and does not rule out field theory. And that seems to me fundamental. Yeah. But I don't think that quite addresses your point, though. But it's in the ballpark. I mean, just one comment. I did ask Anthony Valentini and Philip Pearl on their opinions about did their theories satisfy. So you might be interested. So Anthony said no, it's violated. Mm-hmm. And Philip said yes, it's satisfied.
I think that's right.
Yeah, I think that probably is right. But Anthony's understanding of probability in pilot wave theory is not the normal one. If there is a normal one, I don't know. But anyway, so Anthony, for him, the probability distribution and the physical state here, this physical state, is bound up with some coarse graining of some initial configuration of Bohmian particles. So, and I don't think that's the East Coast picture of probability, but I may be wrong. So I'm very intrigued, actually, as to how this does work out in these two theories. Yeah, that's all.
Well, I guess that's all the questions we have time for. Thanks very much, Mr. Simon. Reconvene at 11. So help yourself.